Okay, so this brings us to the last talk. And so this is also a very different talk from what you have been hearing. It would be more about statistical modeling for some recommender problem. So it's a two-part talk. So first I'm going to introduce you to what I call the classical item recommendation problem. And again, this problem has been worked upon by many people and there is a rich literature, but I want to just give a brief introduction just to make sure everybody's on the same page. And then I'm going to mention some challenges that happen for these kind of problems when you are trying to do recommendation on a social network, like Twitter or LinkedIn or Facebook. I'm going to talk about LinkedIn because I have access to that data, not the other two. And then finally, I'm going to do a deep dive on one of the problems, which is about estimating reputations of users who produce content on the social network, right? And again, this is just an example. The concepts hopefully would apply to other problems as well of similar kind. So here is the classical item recommendation problem. So the goal here is to serve the best items to users in an automated fashion to optimize some long-term objectives, which could be user engagement, revenue in advertising, and so on and so forth. So here is an example. If you go to LinkedIn, there is a module which is called LinkedIn Today. And what this module does is it publishes news articles. It also publishes, it publishes news articles of various kinds. Some of these news articles are things that are shared by users on external publisher sites through the LinkedIn button. So for instance, if you go to TechCrunch and you like an article, you can share it on LinkedIn. And we are going to pick it up. And if these are really good and resonate very well with most of the professionals on our network, we are going to show it here. We also have what are called influencers. So these are reputed people like Bill Gates and the president and other people who actually could write long-form content on the LinkedIn platform. And if an article is shared by someone whom you are following, we'll also show it on this module. So these are the different kinds of content we publish here, and the goal at the end of the day is to kind of recommend articles that are going to maximize some user engagement measured by some metric like click-through rates, right? So the classical problem, and again, as I said, this has been worked upon by many people. So you have a user I, you know everything about the user, not everything, whatever they tell us about the user. We know which industry they are from, what their educational background is, what kind of skills they possess, where they have worked, where they're working now, where they have worked in the past, and so on and so forth, right? And then you have a bunch of articles or items in general, and there is some recommender algorithm that chooses the best item to show, and then the user kind of gives you some feedback, which could be either a click or a no click. And so the question is, given this whole scenario, how do you select which items to show to the user, right? Is it all about getting an estimated CTR and then just choosing the max, argmax, or is there more to it, right? So ideally, yes, you would want to do that, right? If you knew the CTR without any error, you are going to choose the article that has the maximum CTR and serve it to the user. But unfortunately, you never know the CTR without error. There is always a statistical variance associated with your estimates, and how do you mitigate that variance is the key question here, right? So that's the reason why you have to do what is called an explore-exploit strategy, right? So if you have enough data on an article to estimate the CTR without any error, then you just serve that, you exploit whatever you've learned. But there may be many articles in the pool which have not been shown a large number of times, and you're not very certain about its estimate. So you may want to explore those articles. Even though the empirical CTR looks low, you may still want to explore those articles unless you are absolutely sure whether it's a good or bad article, right? So this is the classical explore-exploit trade-off, which one always faces in these kinds of problems. Just to kind of give you a better idea of how this trade-off works, imagine a simplified scenario where you have just two articles in the pool, and the CTR of the first one is 2 in 100. So it was shown 100 times and you got 2 clicks, and the other one was shown a lot more, 10,000 times, and you got you got 250 clicks. So the greedy solution is going to tell you to show article 2 to the entire population. But that may not be a very good strategy because there is more statistical variation in terms for the CTR of article 1 compared to article 2, right? So there is a finite probability that item 1 might be better than item 2. So you don't want to starve this item of further displays. You want to keep showing this at least a few times until you are absolutely sure whether this is a better article than 2 or worse article than 2, right? And so how to do this exploration, how much display should you allocate to this article versus this article is the classical explore-exploit dilemma. And again, you can work out the solution to these things by using classical multi-arm banded strategies, right? So so here is an example of some data which was collected from the module I showed you, right? So these are the click-through rate of different articles that was shown on LinkedIn today, right? And as you can see, there is a lot of variation in the CTR. So it is not the case that a few articles always dominate the rest. And so that's why it's not an easy problem. You know, if you just do naive ranking, it's not going to work, right? You have to do things, some simple explore-exploit algorithm to ensure that you pick up the best article and you're maximizing the total number of clicks you're getting on that module, right? Again, here is a very simple explore-exploit scheme which you can do, right? You take a small fraction of traffic. To that small fraction of traffic, you randomly show articles. That kind of gives you data on every single thing that is introduced into the pool, and then you use that data to learn about the popularity of those articles and choose the one that is best for the remaining 95%, right? So very simple explore-exploit scheme, right? And again, the solution which I was talking about a bit earlier did not do anything about personalization. So if you want to do personalization, there is no closed form or well-known optimal solution to this problem. Often what is done is heuristics, right? So one heuristic could be the same as I described earlier. You always take a small fraction of traffic where we randomly allocate data and then you learn from those. The other heuristic which is often used is if you have a very high dimensional problem when you're doing personalization, right? You're trying to figure out the best article for every single user based on all the features you have about them. You reduce the dimension of the problem, right? And the way you reduce the dimension of the problem is by using some supervised machine learning algorithm and then do explore-exploit in a lower dimensional subspace, right? So again, these heuristics work well in practice. There are some results known about when these things could be optimal, but not very comprehensive. Okay, so that was the classical problem. Now let me come to what is called the feed recommendation problem, right? So if you go to LinkedIn or Twitter or Facebook, so let's focus on LinkedIn here. You know, LinkedIn publishes a feed where we can show many different kinds of content to a user, right? So some example of content, network updates. So these are all updates about your network, right? So if someone in your network changes a job, that is something which I can publish on the stream, right? And if it is a close connection, you might actually want to know where they started working and so on and so forth. If someone completed a job anniversary, that's also something I can show. If someone got connected to someone else, if someone endorses someone for some skills, if someone uploaded a new photo. So these are all different updates which I can show on the stream. And these are all related to your connections in the network, right? And then, you know, if you're following some influencers and if they publish some article, I can show that. If your friend shares an article, that is also something I can show on the stream. If you are following some what we call content channels, say about leadership or Java, and if something comes up, we can show that. If you're following a company, Google, Twitter, and if they publish something, we can show you that. So if there is a new job that has been posted by someone and we believe that job is relevant to you, we can also show those things. And finally, we also show what are called sponsored content. So these are more ads, right? So if a company wants to broadcast a message, and if two people who are not following them, they have to publish it as an ad. And that also can go into the network update stream, right? So the main difference here from the classical item recommendation problem is you don't have a single kind of item which you're recommending to users. It's not like out of all the movies in the world, which one should I show you? Out of all the news articles in the world, which one should I show you? You know, it's a heterogeneous content pool having very different characteristics. Some of them are more influenced by your social connections. Some of them may not be more influenced by social connection. And the challenge here is how do you solve this recommendation problem when you have such heterogeneous pool, incorporating not just the identity, behavioral data that you have about the user, but also the social affinities that viewers have with some of these content producing entities. Right? So that's really the main challenge. Right? And so the approach which we take to this problem at LinkedIn is we take a tiered approach to ranking. And again, this is primarily based on more for scalability than anything else. Right? So, on tier 1, there are different kinds of rankers. So you might have a ranker that produces the top news ranking. You might have a ranker that produces the top network updates. You might have a ranker that produces the top ads and jobs and so on and so forth. So these rankers, when they are called, give out their top K recommendations. And then there is a blending layer, which kind of blends all these different content type and assembles the stream to be the most engaging to the user. Right? So if tomorrow someone else wants to come up with a new content type which they want to inject into the stream, all they have to do is add another ranker over here. And then the blender is going to pick it up. And if it is indeed engaging relative to all the other content that could be published to the user, it's going to get promoted in the feed. Right? So that's the approach we take. So some of the challenges. I'm not going to talk about the solution to this problem today. I'm just kind of outlining the challenges. Personalization. So the usual personalization when you don't have a social network, we all know how that works, right? You kind of collect all the information about the user and then use it in your machine learning model. But when you're dealing with social network, a viewer's affinity to what we call the actor, right? The actor is someone who can produce content. Like if you are changing a job, you're actually producing a content, right? Estimating these affinities and also for different kinds of updates is a very important problem. So I might have a very strong affinity to my friend when it comes to them changing their job, but I might not like the articles that they produce, right? So the affinities can be different for different kinds of updates, and we have to estimate these things in a statistically reliable fashion to be using it. Then there are effects like frequency discounting, right? So if you see the same update multiple times, you kind of get bored and you don't want to see it again. So we have to make sure that is there. The content should be fresh. This also depends on the kind of content. If your friend changes a job and if you have not seen it, even if you know it after 7 days, that's fine. But if there is a news article and if you know about it after 7 days, that's not fine, right? So the degree of freshness which you need to have for different kinds of content, right? And then diversification. When you're assembling the stream using different kinds of content, you don't want to show all jobs on the first 3 slots. Even though there may be awesome jobs, and you are actually interested in seeing a job, it is better to mix up things, right? So if you're showing a job on slot 1, maybe you want to show something else on slot 2, right? There are multiple objectives that one has to adhere to when you're assembling the stream. So if you're showing an ad, you want to maximize revenue, but at the same time, you don't want to show ads that are jarring to the user. You want to make sure that the engagement is also preserved. A/B testing, right? So whenever you're rolling out a new methodology to the stream, you want to run a bucket where you allocate the new algorithm or you serve using the new algorithm to a random population, and then there is another random population that is the control group. However, when you have a social network, there could be spillover effects, right? So if I get a new algorithm and I start sharing a lot of articles because it is popping up in my stream, those articles would then become candidates that could be shown to my friends who are in the control group. Right? And it's not very clear whether the impact of the new algorithm is better than the control when there are such spillover effects. Right? So one needs new methodology to do A/B testing when there is such interference going on between populations. Right? Engagement metrics. Right? So users engage with the stream in different ways. Right? They might click on something. They might congratulate a friend when they change a job. They might share something. How do you take these different actions that users have on the stream and combine them and come up with a function which is representative in some sense of their long-term engagement on the site, right? So that's another challenging problem, right? And finally, this is something which I'm going to talk about a little bit in whatever time I have left. There are many users on the stream who are producing content, right? So when you're sharing something, you're actually producing content that can be broadcast to your network. Can I use those kind of data to estimate your reputation, for instance, in a given topic, right? So if you produce articles, say, in Java or algorithms that are liked by the population at large, that means your reputation for that particular topic should be high. And once you can compute such reputation scores, that could be used in various places on the site to improve results, right? So I'm going to talk about this a little bit more. And finally, summarization, right? So as I mentioned, we are free to inject new kinds of content into the stream, right? I might come up with a content, something like top articles read by CXOs in the last week, and create a stream like that, or create a content summary like that and start injecting into the stream, and it might actually resonate very well with the user. So this is a new kind of problem, right? When we are talking about algorithms or machine learning, we always assume there is a given problem and there is an objective function. You have to maximize that. Here, this is a more open-ended, somewhat related to clustering problem, where you can actually take whatever content we have on our ecosystem and create attractive summaries out of those, and then show it to the user and see whether it works or not. So that's another open problem, I feel, that have not been tackled in the past. Right? Okay. So these are some plots. So I was talking about the impression discounting. So this is what happens. So if a user sees the same update multiple times, the CTR keeps decaying. Not very surprising. I mean, this is an effect which I believe most of us have seen when we're working with problems like that. How does the response rate change? So this is how the response rate changes. So this is showing the effect of diversity, right? So if the same update type have been seen by the user in positions above, in positions above what we are focusing on now, then again the CTR decays, right? So if you see 3 jobs in the first 2 positions, then your CTR on the 3rd position is going to go down compared to if you don't see any job, right? So this kind of shows that diversification of diversifying recommendations among different types is also very important, right? And again, finally, freshness. So freshness again depends, right? So if you're looking at content like anniversary, yes, freshness matters. But if you're looking, if someone commented on something and you show it even after 7 days to your friend, it still kind of works pretty well. So freshness depends on what kind of content you're looking at. On Twitter, maybe when you're sharing links, freshness matters more. But on LinkedIn, there are some that are time sensitive, others are not, right? And we have to figure out which one of these are time sensitive, which one these are not. Okay.
The x-axis here?
Pardon?
The x-axis?
The age in hours.
In hours.
Yes. Okay. So 5 minutes. Okay. So let me just go through a particular problem, and again, this is something I call estimating reputation of a user in a given topic. So reputation in this case is defined as the likelihood of a positive response by an anonymous user to an article shared by a user, right? So your reputation in algorithm is the propensity of an anonymous user whom you don't know to click on the article that is shared by you, right? So that's the reputation. Now this is very different from what is called influence that have been studied in graph theory quite a bit, right? If you share an article, how quickly does it diffuses, or what is the reach of your share in the network is what is called influence in general. But reputation is different, right? This is how will a user who is not connected to you would respond to a typical article that is produced by you, right? And so it's not very easy to estimate this reputation from the network data we have, because the network data is biased, right? And again, here is an example of why it is biased, right? So, there is selection bias. So whatever you share is only shown to the people who are connected to you. And again, there is also response bias, right? So if you're a grad student and if your advisor is sharing something, then you are more likely to respond to it, just out of politeness, I guess. So that also creates bias in terms of reputation. So maybe your advisor is not very reputed in a particular topic, but may start looking reputed because he has a lot of students, which is not the right reputation score. Okay. So here is one approach we took. So the idea here is, how do you debias the data? So the way we do it is as follows. So the goal here is, can we collect some ground truth unbiased data on reputation? Again, this ground truth data cannot be available in large quantities. It would be available in some small quantities in some aggregated form, and then combine that with all the network data and then kind of debias things, right? So that is the main idea here. And so here is an example. So on LinkedIn today, when we are showing an article, you as a user don't know who are the people who actually shared these articles. There might be 5 people who actually shared this article from all over the web, but you don't know who they shared it. You click on the article if you like it or you don't like it, right? Whereas on the stream, you know who is sharing the article and you're responding based on both the quality of the article and perhaps who the sharer is, right? So this is in some sense an unbiased data and this is biased. Can we combine both and come up with a unbiased reputation score, right? So you can do something like this through some statistical model, right? So again, this is, I'm not going to go through all the details, you can read it in the paper, but the main idea here is you are getting some response. So J is the article, I is the user. So you're getting some response to articles on the unbiased, on the LinkedIn Today, for LinkedIn Today, which is more unbiased. And again, this response is a function of the popularity of that article in that particular topic, right? And so now there is a latent model that is assuming that the popularity of an article in a particular topic depends on the reputation of the people who are sharing those articles. If there are 5 people who shared the article, then the popularity of that article on LinkedIn Today is an average of the reputation of people who shared this article, right? So this is something that is latent. You don't know. The goal here is to estimate this quantity, which is the unbiased sharer reputation here. And then on the feed, you can also say, well, the probability of responding to article I by user J when it is shared by user S is also a function of the reputation of the user, but again, this is biased, right? Because there's all kinds of response biases and selection biases over here, right? So now the question is, how do you connect this with this? This is really the crux of the problem. Can I get an estimate of this by using this data, which is kind of meager, and using information here, right? Can I kind of transfer information here and here to kind of get an estimate of this, right? And you can do that. I mean, this is one way of doing it. So you kind of say, okay, well, the unbiased reputation score is connected to the biased reputation score, which can be estimated very reliably because I have a lot of data on the stream through some regression function. Right? So you can regress this with this, and then this kind of leads to debiasing the data. So I'm not going to go through those other details. I mean, there are some other details here, but that's the main idea. Connecting the sharer reputation, which you're obtaining from the unbiased data with very sparse data with something which is biased, and debiasing the whole process through some linear function. Right?
So, question.
Yeah.
So that the previous thing there, so the alpha SK is your bias term.
Yes.
So that's saying that there's some bias associated with a particular sharer in a particular topic.
Yes.
But there's also people who just sort of share indiscriminately. And you kind of want to debias the fact that someone just shares all the time. So that would be a different kind of bias.
Yeah, so in this function, I ignored this part. So one of the feature could be just to have one, right? So there will be some main effect, and then there will be some other effects based on the users.
You model that as well.
Yes. It is implicit in this. I didn't go through the detail, but it is implicit in this, yes. But that's a good question, yes. Right, and so we, okay, so this is all great. Now, how do you know it is actually working, right? Again, these things are very hard to evaluate in practice, but we did some rough evaluation. So the way we did the evaluation was, and I'm running out of time, but let me just explain the evaluation. So we took some, as usual, some training data and some test data, right? Okay, so this is what we do. So we took data in some time period and create these unbiased reputation score using the model. And then what we do is we take out some users in the training data and see what the average click-through rate was on LinkedIn Today for articles that were shared by them in June, right? So May is the training data, June is what was the average click-through rate for articles that you shared in June, right? So this is your test data. Now if the reputation score produced by method A is highly correlated with the average click-through rate of articles that were shared by you on LinkedIn Today in June, then that means that's a better method compared to something else where the correlation is weak, right? So that is the evaluation method we used, and you can see, so we compared it with different PageRank algorithms. PageRank algorithms are supposed to estimate influence rather than reputation, right? So as expected, the PageRank algorithms do not have enough correlation with this at all, but if you kind of do the debiasing the way I described, you start getting good results in terms of correlations, right? So again, this is just an example of how you can utilize information in the social networks and combine it with some other ground truth to kind of come up with very nice estimates of things which you would like to have, but you cannot get just by using the social data, right? Like I say, I'm out of time, but just a few takeaways. So recommendation problem, as I said, in a social network are challenging, and I kind of outlined all the challenges before by using the example of feed recommendation. And again, I discussed the estimation of an unbiased sharer reputation today, but several other problems I believe can benefit from this approach. Because, for instance, if you are looking at endorsements on LinkedIn, endorsements are also biased, right? I mean, people who are connected to you might endorse you more than people who are not connected. So if you have very high degree, you generally get more endorsement. That doesn't mean you are really an expert in that particular area. But can you crawl the web and get the H index of authors, some small set of authors, and kind of have that as a ground truth, and then combine that with the social data, let's say on LinkedIn, and come up with a better unbiased estimator of reputation, for instance, right? I mean, that could be one example of how you can use these techniques. Now, of course, the modeling would change quite dramatically. It would not be the same model, but the ideas could still go when you're solving problems like that. Okay, so with that, I'm sorry I went a little late. Thank you.